Hello everyone, good morning. I'm Mingxing Xu from Tsinghua University. I'm glad to have a chance to share some ideas for this challenge. Here is the outline of my talk. I will present to you 5 parts. As we all know, effective computing for video has a large number of applications. For example, video indexing, recommendation, and so on. And in computer vision research field, a natural further step of computer vision is to endow computer with human-like perception capability, especially for emotion. So this year, the emotion impact of movie task consists of 2 subtasks. The first one is to predict the dimensional valence and arousal score from the consecutive 10-second segments. And the second one is to predict the fail. So this function is very useful to protect the children from potential harm video content. The experiment data are selected from a public database, THUHCSI database. It contains 160 movies. There are 30 movies are selected for the development set, and 14 movies are selected for the test set. Because the organizer have provided the baseline feature set, they extract the emo base with OpenSMILE for audio, and the visual features consist of CNN features and other visual features, maybe the local duration of the video. So here is the approach of our approach to the subtask 1. We extract the eGeMAPS as additional audio features. Because we did this task last year, we found that eGeMAPS is good enough for the emotion recognition. And we concatenate all the short baseline visual features as a whole vector except CNN features. And finally, we normalize all the features into one vector with zero mean and unit variance. In our research, in our approach, we have evaluated the 2 different kind of models. The first one is non-time-sequential models. There are 2 models: support vector regression and eta boost. The time-sequential model, we select LSTM. Here, we regard the LSTM as a regression model, just sequence to 1. The input of the LSTM is the features extracted from 10-second slide window with 5-second overlap. And we also evaluated 2 different fusion methods. The first one is early fusion, is denote the calculating all the short visual features. This is just fusion at feature level. And another one is native fusion, to combine all the outputs of different models at decision level. So for the native fusion, the SVR and the eta boost is just simply averages the predictions of different models. And for LSTM, we trained a 1-year full connected network on validation data to output the final output. Okay, so in our approach, we have post-processing. So in this phase, we use a triangle field to smooth the output. So for the field direction prediction task, we use the same features as the subtask 1. So here is there is a bigger challenge, a bigger problem. So the data is very unbalanced. So we will see the proof in the experiment results. And so, considering this unbalanced distribution, we use the smart algorithm to generate new samples for the minorities using interpolation. Okay. And because the unbalanced data distribution, we only tried the one model, random forest. And, in fact, we tried others, but we found the random forest is the best on validation data. So we submitted 5 runs, just use the random forest. And we also tested fusion methods for the subtask 2. The first one is concatenate features at the feature level, and another one is native fusion, just like subtask 1. Okay. So here is the details of our experiments for the task 1. So we submitted 5 runs. The first one, run 1, is LSTM trained with one kind of features. For valence, 2-layer LSTM trained with eGeMAPS, and for arousal, 3-layer LSTM trained with VGG. We trained these LSTM models for valence and arousal separately. They did not share any hyperparameters. And for round 2, we use native fusion to combine 3 different LSTM. The LSTM trained for valence, the eGeMAPS, VGG, and other visual features. And for arousal, eGeMAPS, EMO-base, and CEDD were selected to train the LSTM for arousal. We combined the outputs of these 3 LSTM to output the final results. This is round 2. Round 3 and round 4 are just classic models. Round 3, we use SVR models and train with VGG features. Round 4, we use AdaBoost, and we select eGeMAPS for valence and other visual features for arousal. Okay. Finally, we combine the round 3 and round 4 as the round 5 to submit. So here's the details of the output results. We can see for the MSE of valence, the round 2 gets the best performance. This means the native fusion can work well for the valence prediction. But if we look at other metrics, so we found the classic model, round 3, SVR model trained with VGG, has the best performance. Okay, so if we compare the round 1 and the round 2, we can conclude that the native fusion is better than early fusion. Okay. So here is the details for the experiments in subtask 2. We also submitted 5 rounds for this subtask. Just I mentioned before, only random forest model was adopted to this subtask. Round 1, we use random forest trained with other visual features. And round 2, we trained the model with VGG features. And round 3, we trained the model with all the visual features provided by the organizers. Okay. And round 4, just you have seen in the lecture per PPT, we just designed a test run to predict all the test data as 0. This means no fail. Okay, so we can get the performance of this run. Next slide. Finally, we submitted the round 5 to combine the round 1 and round 2. Here is the details of the performance. We can see for run call and recall and F1, the round 2 method has the highest performance, and the combination native fusion for accuracy and precision has the performance is the best one. So finally, we draw the conclusion. So VGG features contain useful information for video emotion analysis, outperforming other features. As a whole, classical models, as they are for subtask 1 and the random forest for subtask 2, achieve significant performance, illustrating their effectiveness. However, there are some remaining problems. We want to do this work in future work. Okay, that's all. Thank you very much for your listening.